All right. Thank you very much, Dr. Khanna. And my name is Christopher Gilbert, and thank you for coming to my presentation on the demonstrating the causation of gravity for subluminal velocities. So what do I mean by subluminal velocities? Now, first of all, it's not subliminal, it's subluminal. So basically anything slower than c, or anything slower than the speed of light, or in this case where the velocity is much slower than c. So we're not talking about photons traveling at the speed of light. We're talking about basically human speeds. So this gives us a way of looking at gravity that we experience. So, and here on Earth, of course, we have a weak gravitational field. So we're not talking about being near a black hole like what's right behind me. We're talking about a weak gravitational field here on Earth and a static gravitational field. So what I mean by that is basically just that from 1 second to the next, it's not changing, it's not evolving. It's going to be the same gravitational field last second as it is next second as it is this second. So we don't have to worry about it changing with time. It's going to be the same thing. And again, weak and at human velocity. So really we're looking at what is the cause of gravity that we experience as humans. So first, let's start out by looking at Einstein's field equation. And basically that looks like this. So you have big G mu nu, which is actually Einstein's tensor, is defined by r mu nu minus 1/2 r g mu nu equals 8 pi big G over c to the 4th t mu nu. Now, one thing I'm not going to do is I'm not going to actually try to explain everything about this equation, because honestly, half of you won't understand what I'm talking about, and the other half of you will probably think I don't understand what I'm talking about. So let's just leave it at this. It's curved space. This is what the equation tells us, is that space curves, and that gives us gravity. So let's look at the scale of some of the most massive objects in the universe so we can get an idea of just how much curvature of space we're talking about for different objects. So for example, the sun over here, and forgive me, my mouse doesn't like to work. So the sun over here gives us just a little bit of space curvature, just a nice little gravitational well. We get to something a lot more massive like a neutron star, and we get a much deeper gravitational well, a much deeper curve. And of course, with something like a black hole, especially a supermassive black hole, we actually get a lot deeper gravitational well, like really extreme gravitational well, something really deep and curvy. But actually, 5 minutes ago, there was a massive scientific discovery. There are actually more massive objects out there. I don't even think Dr. Khanna knows about this yet. There's more massive object out there than even the most supermassive black holes. So what we're talking about here is actually the rubber sheet model. The rubber sheet model basically shows essentially mass curved space. And in this particular image, we have this mass in the middle, this larger mass that's in the center, that's kind of sinking into our graph. That graph represents space, and it's sinking into space, it's curving space. And objects that are orbiting are basically traveling in a straight line. They look like they're curving, but they're actually traveling in a straight line. But what they're doing is those straight lines are following the curvature of space. So it's going to go around the curvature as it's traveling in a straight line. Oh, wait, something isn't right. What do I mean something isn't right? Well, first of all, I mean, this image alone, the rubber sheet model, it gives you the idea that it's space that curves. And this is a misconception, and it's a major misconception in general relativity that is confounded by a couple of things. And the first thing it's confounded by is that the truth is much more complicated than that. And of course, you know, as physicists, we tend to just say, yeah, it's space that curves, because honestly, as physicists, we just don't feel like explaining it to you. But I will. So first of all, it's space-time. It's not space, it's space-time. General relativity actually explains that space and time are one and the same thing. You can't have space without time, and you can't have time without space. So basically, it's space-time, not space and time. They're inseparable. You cannot separate them, except mathematically, you can separate them with the Schwarzschild solution. That allows us to actually look at the different effects of the warping of time versus the curvature of space. So even though we've always said, oh, it's space-time, you can't separate them, well, we kind of can in the equations, but when we think of space and time, it's space-time. So here's the thing. At the speed of light, the curvature of space does have as much of an effect on gravity as the warping of time. So if you're a photon traveling through space-time, the curvature of space and the warping of time are going to have equal effects on you, and that's why light curves, is because it is following the curvature of space and the warping of time. So the simple answer, or the comfortable lie we often give layman is just that, yeah, it's the curvature of space, because again, it's much more complicated and we don't feel like explaining it to you. However, we don't move at the speed of light. And that's important because at human speeds where, you know, you have a slow velocity, you have a weak static gravitational field, space is flat. No, not the Earth. Space is flat. So what is the cause of gravity at the speeds that we experience, at our human experience? What is the cause of gravity? Well, let's do some math, okay? So first of all, let's start with the Einstein field equation again. You have G mu nu is defined by R mu nu minus 1/2 R G mu nu equals 8 pi big G over c to the 4th T mu nu. Again, I'm not going to try to explain that. So let's look at this. First of all, we're going to look at this G mu nu right over here, this little G mu nu. That's actually our metric of space-time. That's going to actually define just how much strength and curvature of gravity kind of, there's some other things that mean that too, but that's really what we're going to look at, how much gravity or how much curvature is affecting gravity and stuff like that. So we're going to look at what is the metric in this room. And by this room, I actually mean the difference between the floor and the ceiling. Now, we're only in like maybe a 1.5, 2 meter room. In a few minutes, we're actually going to deal with a 10-meter high room because that's about what we can measure. But in this room, we can actually calculate the difference between the time on the floor and the time on the ceiling. But there's an interesting thing that's going to come up, that a meter on the floor is the same meter on the ceiling. A second on the floor is not the same second on the ceiling. So let's look at that a little bit. Again, weak static gravitational field with slow velocity. This is what the metric looks like. So G mu nu actually equals eta mu nu, which is your Euclidean metric. So that's a simple -1, 1, 1, 1 in a triangular Kronecker delta kind of thing, plus a small perturbation. So H mu nu is our perturbation. And what I mean by small is that the absolute value of H mu nu is much lower than 1. So it's small. All right, so let's skip over to the geodesic equations for a moment. And this is actually very simple. And I apologize to those of you who maybe freshmen or sophomore or even some juniors that might not get some of this math as we go on. Honestly, if you have never been to a physics conference before, get used to it. So what you have in the geodesic equation, basically, the first phrase, this d squared x alpha over d tau squared, is basically just your acceleration. But then we actually have this connection coefficient, gamma alpha mu nu, basically times your 4 velocity. And so what I want to worry about is your 4 velocity. Now, again, it's the acceleration, the connection coefficient, your 4 velocity equals 0. But I want to look at these 4 velocities for a second. And really what I want to explain about 4 velocity, it's a little more subtle than this, but all it is taking your velocity, which is normally your change in distance or your change in x over your change in time, and we're going to break that up into, first of all, your normal 3 dimensions. So it's going to be x, y, and z instead of just x, but also your 4th dimension, which is time. But we're going to put that 4th dimension first. We're going to put time first, and then we're going to have x, y, and z. So 0, 1, 2, and 3 are going to be time, x, y, and z. So let's take a look at that, because where u is your velocity, u lambda is going to basically be gamma times c for time, gamma u x for x, gamma u y for y, gamma u z for z. And one of the things that happens when we consider, again, velocities that are much slower than c, as we see over here, your absolute value of your velocity vector is much slower than the speed of light. Well, if we look at gamma is actually 1 over the square root of 1 minus your velocity squared over your speed of light squared, then you notice that if you have, say, maybe 1 meter per second squared, not second squared, but 1 meter per second squared over 300 million meters per second squared, that's a huge difference there, because now you've got 1 over 10 to the 17th. I mean, you've got a really small number, really small. It might as well be 0. In fact, we actually look at that for when we're finding the limit of something divided by 0. So basically, or no, other way around, something divided by infinity. So basically we're going to end up with 1 over the square root of 1, which is 1. So gamma goes to 1. So essentially, and again, if your velocity is much lower than c, we might as well actually consider it 0. You end up with gamma times c is 1 times c. So your time is c, your x, y, and z are all 0. And what does that mean? Therefore, that the mu nu are each going to be 0. So mu is 0 and nu is 0, because if they're anything else, they're going to equal 0, or, you know, your value is going to equal 0. So mu and nu have to be 0. Also, d tau, which is basically your proper time. Again, that's time at like infinity, or basically in the reference frame that's not moving. It's time that's not really changing, but we're comparing that time to the ground time and saying the ground time isn't changing. So in this equation, d tau equals dt over gamma. Gamma equals 1, so d tau equals dt. So we can just do a quick, easy substitution there. We end up with actually the second derivative, or acceleration, in your spatial velocity, or your spatial acceleration, plus your connection coefficient. But now the correct connection coefficient is going to be gamma alpha 0, 0, because again, mu nu is 0, 0, times c squared equals 0. So it's getting a little simpler now. It's still kind of complicated, but we're kind of, we're taking a little off it. So what is that connection coefficient going to equal? So your gamma alpha 0, 0 ends up equaling -1/2 g alpha sigma h 0, 0 and a partial derivative of sigma equals, and I'm substituting here the eta alpha sigma in for the g alpha sigma because they're basically at this point kind of the same thing. So you end up with -1/2 eta alpha sigma times h 0, 0 in the partial derivative of sigma. Now let's look a little deeper here, because there's no gravity in x or y. You don't fall sideways, you fall down. So there's only gravity in z. So we can immediately assume that we don't have to worry about alpha being 1 or 2. We know that alpha can be 3. So if that's the case, and we know that eta alpha sigma is essentially the Kronecker delta alpha sigma, which means that if alpha doesn't equal sigma, you have 0. And so in the case of eta 3, 3, you end up with 1. So very simple. So now we can actually eliminate that because it gets a little easier now. So now I've also taken the x alpha out, and because we're only dealing with the z direction, we're going to have the second derivative of z over dt. And so you're looking at your acceleration minus 1/2 h 0, 0 partial derivative of the third slot, or z slot, c squared equals 0. Okay, so we're getting a little bit better, a little bit easier to understand. So let's do a little algebra here. We actually have our acceleration in z equals 1/2 partial derivative of h 0, 0 over partial derivative of z times c squared. Well, what is your second derivative of z? That's your acceleration down. So that's really your acceleration of gravity. And here on Earth, we know the acceleration of gravity. It's little g, or minus little g in this case. So d squared z over dt squared is simply -g, or as we know it, 9.8 meters per second squared. So let's just solve for h 0, 0 now. So h 0, 0 is going to equal -2gz over c squared. That's going to come in really important in just a moment. But let's look at h11, h22, and h33, which all equal each other and all equal 0. That's easy. So we don't have to worry about that. We only have to worry about h 0, 0. So, and if you recall, I mentioned earlier that g mu nu equals eta mu nu plus our perturbation of h mu nu. So we end up with g 0, 0 equals the negative of 1 plus 2gz over c squared, but g11, g22, and g33 just equal 1. Again, nice and easy. So let's look at that Schwarzschild metric again. So the Schwarzschild metric was actually, he was pretty cool. He derived and solved Einstein's field equations in the trenches of World War I, literally, and then died. Sorry. But anyway, that was a pretty cool thing. He had bombs dropping around him, bullets flying over him, and he was able to actually solve Einstein's field equations on a piece of paper with a pencil. I can't even do that with a computer. So, but let's look at what the Schwarzschild metric basically is. It's going to be ds squared, which is kind of like just your interval. Basically that's your interval of space time. So ds squared equals g 0, 0 c squared dt squared plus g11 dx squared plus g22 dy squared plus g33 dz squared. But we know that g11, g22, and g33 are 1, so we can eliminate those. And if we look at the metric in the room, then we end up with ds squared equals negative of 1 plus 2gz over c squared times c squared dt squared plus dx squared plus dy squared plus dz squared. So it's not that complicated anymore. It's actually pretty simple to look at. So let's look closely at this equation. I want to take a look at this dx squared plus dy squared plus dz squared, because that means space is flat. There's no curvature to it at all, at least not in our experience. So there's no difference between a meter on the floor and a meter on the ceiling. It's the same thing. Space is basically flat. So let's take a look at the time component of this equation, where you have negative of 1 plus 2gz over c squared times c squared dt squared. What does that mean if space is flat, but we have this warping of time going on? What does that mean for our cause of gravity? The warping of time is what causes the gravity we experience, not the curvature of space. Wow. So apparently it's not the curvature of space. You've always been told it was the curvature of space. It's actually the warping of time. That's pretty major to really grasp. That's something that, you know, it blew my mind the first time I heard that. So keeping that in mind, let's take a look at a new version of the rubber sheet model. Kip Thorne actually modified the rubber sheet model to use not only the curvature of space, but also the warping of time, where color in this, say, the color scheme represents the warping of time. And so we have that spectrum of color going from violet all the way to red as time slows down. And that basically gives you like the red shift. And this actual image, this particular rubber sheet model that he has here is, it's an extreme mass ratio infall, or we call it an EMRI, as you may have heard in some of the other like NERS talk earlier. So this is a really, really, really cool image because it gives us an idea of the kind of gravitational warping of space and time that we get from two supermassive black holes falling into each other. So let's do a little punch and crunch now on that metric in the room we were talking about, so we can get an idea of just how much the time changes, the flow of time changes from the floor to the ceiling. So to set up some givens for you, we're going to set h. I'm getting rid of the z because we're only dealing with one direction, up and down. We're going to call it height. So h is 10 meters. Little g, of course, is 9.8 meters per second squared. We're going to just round that to 10 just to make it an easier calculation because it's essentially 10. And then, you know, c squared, c, the speed of light, is 3 times 10 to the 8th meters per second, or 300 million meters per second. And of course, the time on the floor, we're going to use 1 second, because it's just going to be easy to see the difference between 1 second on the floor and how much time is actually passed on the ceiling. So, and remember again that d tau equals the square root of 1 plus 2gh over c squared times dt. So what is that? Well, d tau is going to actually be your time on the ceiling, and that equals square root of 1 plus 2gh over c squared times the time on the floor. And the time on the floor, of course, is 1 second. Well, that just got easy. So now we can just substitute in all of our g and h and c, and we get the square root of 1 plus 200 over 10 to the 17th. And 200 is basically 10 to the 2. So essentially what we end up with for an answer is basically 1 plus 10 to the negative 15th seconds, or 1 femtosecond faster on the ceiling than on the floor. So that's pretty amazing that we can actually calculate that from 10 meters up, it's 1 femtosecond faster than the time on the floor, on the ground. That's really, really cool. There's some experimental evidence that actually has proven this, or basically proven it not wrong yet, but what that experiment was, the Pound-Rebka experiment in 1960, was actually done at the Harvard University's Jefferson Tower. They actually had a height of 22.5 meters, so a little over double what we actually had of 10 meters, but you'll still see how it works out. Of course, they were using the Moss-Bauer effect. Don't ask me what that is. Ask Dr. O'Reilly. I have no idea. Measured their GH over C squared to be approximately 2.5 times 10 to the negative 15. Now, if we go back a little bit to, we were talking about here, the square root of 1 plus 2gh over c squared. So gh over c squared is really the important number. And we said that was 200 over 10 to the 17th, so basically 10 to the 15th. So where they were double our height, they got, sorry, a little bit over double our actual time difference. So, but the 10 to the 15th being the important thing that we need to look at here. That basically is not only being able to calculate a femtosecond difference over 10 meters between the floor and the ceiling, but actually measuring and proving that both the calculation and the experiment predicted each other perfectly. Well, almost perfectly, but enough to be able to say that is Awesome. That confirms Einstein's general theory of relativity. But we actually have experimental evidence that pops up on a daily, if not every second kind of basis. Oh, actually, I'll come to that in a second. First, let me show you a quick explanation of their experiment. So, from the floor, you can see that the clock is actually a little slower than the clock that's up here on the third floor. But the experiment that they ran basically was firing gamma rays up to the ceiling and measuring the difference in redshift, and that was able to give them the 10 to the 15th 10 to the negative 15th seconds, or 1 femtosecond. So that's a really cool experiment that they did. But I want to talk about that experiment, the experimental evidence that we get every single day that confirms Einstein's relativity. And it's what makes general relativity the second or third most experimentally or evidentially supported theory in science history. I'll give quantum mechanics that one. They're number one. But general relativity and special relativity are number 2 and 3, I believe. Evolution's like 4. But the global positioning system. GPS is actually designed to compensate for relativity. So we actually have to subtract 8 nanoseconds per day for special relativity, because it's actually staying in orbit. It's actually moving very fast, because it's a good, I think, 20 or 30,000 kilometers above the surface of the Earth. It's got to move pretty fast to stay up there. And so special relativity does actually come into play over the course of a day. You have an 8 nanosecond difference for that, and then a 46 nanosecond difference because it's so high off the ground for general relativity, giving you a total of 38 nanoseconds per day that we have to compensate, or your nav would actually accumulate more than 14 kilometers discrepancy every day. So 14 kilometers, I know we work in the metric system, and some of you professors may have gotten used to it to the point where you can actually visualize in your head just how much 14 kilometers are. Those of us that are still undergrads or almost not undergrads are still kind of, we got to think in miles once in a while, because 14 kilometers isn't that easy to always convert to what we're used to. Let's just remember that in a week, that GPS would be off by approximately 61 miles. So how far is that? Well, if you were centered at UMass Dartmouth and you were looking at your GPS and it had been a week and there was no compensation, wow. So you could be in Salem, you could be in Worcester, you could be in New London, Connecticut, you could be in Montauk, Long Island, New York, or you could even be in the Atlantic Ocean off the coast of Cape Cod, at least according to your GPS when you're sitting at UMass Dartmouth. So that's a pretty big gap. I know, 60 miles, we can drive 60 miles in an hour, but that's a pretty good big gap. So looking at this graph, this actually shows how much of an effect that we get from general relativity versus special relativity at different altitudes of orbit. So the ISS, for example, gets more of a special relativity than a general relativity effect because it's much lower at orbit. It's only about 300 or 400 kilometers up, versus GPS is about, I think that's 30,000 or so kilometers up. So it's 38 nanoseconds different and more general relativity than special relativity. So in conclusion, what I want you to take away from this talk is A, at human velocities, space is flat. Earth is still not flat. Space-time is separable mathematically using the Schwarzschild metric. A second at 10 meters up is a femtosecond, I spelled that wrong, femtosecond faster than it is on the ground. And that's a major difference for only 10 meters. Everybody thinks, oh, the curvature of space-time is over like light years, right? No, 10 meters, we get a femtosecond difference. And of course, the cause of gravity that we feel as humans is the warping of time, not the curvature of space. So when people ask us, what is the cause of gravity? We really should be saying the warping of time. But again, it's too hard to explain sometimes. And most important thing, Einstein was wicked smart. I mean, he figured this out with a pen and paper, or pencil and paper. I can't even do it with a computer. So him and Schwarzschild are in a whole nother level than most of us. That's it. Thank you very much for coming to my talk. These are my citations. I just want to give a special thanks to the Massachusetts Space Grant Consortium, the UMass Dartmouth Physics Department, including all the professors, rather than single you guys out. The UMass D Gravity Group. I loved going to the meetings, hearing about everybody's research, never really having much of an update myself, sorry. The APS D Grav, and my family and my fellow students. Any questions?